Greetings, everyone. Welcome to Lecture 5 of ECE 141 Digital Communications. And in this lecture, you're going to be learning about types of digital modulation with memory. So recall what we have discussed in the previous lecture. We have ASK, PSK, FSK. We have also QAM, QAM, etc., etc. The problem with all these is that if you look between two symbols, right? The transition between two symbols, as you see here, 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 there's a discontinuity in our transmission. Right? Abrupt changes that causes some leakage. Okay? It's not good. So what happens, depending on the pulse that you use, some of the spectrum could leak out of the frequency band. Right? The presence of these abrupt transitions would lead to that. So for example, if you use a rectangular pulse, you have these large side lobes right here at these levels. So it's around negative 15 decibels. If your maximum value is 0 decibels, it's actually quite large right here. So there's a form of leakage from your frequency spectrum, and that's bad. So maybe we can use a half cosine pulse and reduce that right here, but there's still leakage all over. And that is because there is an abrupt transition in your signals. Okay? That's where modulation with memory come into play. Right? The abrupt transitions can be removed, right? And basically, your current symbol B sub L, okay, your current symbol B sub L is dependent on past outputs and the current input. Okay? So basically, your B sub L is a function of your current input and what we call the state of your system. So the state of your system depends on how much memory you have. Normally, we define the state as the past, the current, and the past L-1 outputs of the modulator. Okay? We can illustrate that with some example. Let's say we have a system with memory. You should remember this. Using a D flip-flop, we can actually have some form of memory. So every time that the clock triggers, it stores the current value at the input D. Okay. So let's say we start with both the input AL and the past output BL-1 as 0. So this function right here is the XOR. That means if you add them, then you get a 0 also. The next trigger of the clock, we have a new input, and this will be copied to your previous output. All right? And we add that. There you go. The XOR of 1 and 0 is 1. So for the next clock trigger, BL will be copied to the previous state. We have a new input. Let's say it's also 1. We want to add that. We get 0. All right? So again, we copy that. Now the next input is 0, excuse me. You add that, it's 0. And so on and so forth. And you got that. And finally that. Right. So this modulation scheme is that what happens is if the current input is 1, the output will transition into a different state. So you look at here, it's initially at 0. Once we have an input of 1, your output would transition into a 1. If you have another input 1 right here, the output transitions to 0. And once it is 0, your output does not transition at all. We call this the NRZI signaling scheme. So this is a baseband signaling scheme. So this is a class of non-return to zero signaling scheme that has memory, specifically a memory of 1. So the memory is equal to 1. The best way to portray a system with memory, or what we call a finite state machine, FSM, is through the use of what we call a state transition diagram. So it portrays the behavior of the system if it has finite states. So that means it has a limited integer number of states. For a digital modulation memory, the number of states depends on the number of bits per symbol and the memory of the system. Correspondingly, it becomes this expression right here. So at a given time index L, the current state is also a function of the current input and the previous state. So in the previous example, our D flip-flop is only, the current state is only defined by B sub L. Okay, so from the transitions earlier, let's look at how the machine behaves to the state diagram. This is the state diagram of the D flip-flop. Okay, we define the initial state S sub 0 as when BL is 0, and this is when BL is 1. Okay, so initially we're at the 0 state. If we add that, we are in the 0 state. So this is defined as the state. Okay, this defines the state rather. So now the transition is that when you have an input of 1, it will go through this transition, okay? And then you end up in state 1, right? And the output correspondingly is also 1. Next is the input is still 1, so we trace that. We look at this. This is where the input is 1. It goes through this transition right here, and the current state is 0. Right. So now the input is 0, therefore we look at this transition, then basically the state will go back to itself, and the current state is still 0, and so on. So the input is 1, the output is 1, you have your current state at 1, so on and so forth. Okay, so that's how you form your state diagram. Okay, that's how you form your state diagram. But we're just looking at baseband signals with memory, like NRZI. How do we transmit something? Right? We transmit symbols with memory. So even if we have some form of memory in our NRZI, it's just still a baseband transmission. How do we transmit it through a passband transmission? That's where we have the continuous phase frequency shift keying. Okay, so it's still FSK, but instead of having discontinuities, each time your signal is continuous. So where does it start? First, we will consider a PAM signal. So this is actually the structure of a PAM signal. Your A sub n is the amplitude, okay, at the time t is equal to nt. So the amplitude at t is equal to nt. And g of t is a pulse with duration t and amplitude 1 over 2t. Okay, so an example of your g of t would be a rectangular pulse. So it would be from 0 to t, and its amplitude would be 1 over 2t. Okay? So if we use this as the input to a frequency modulator, we get this expression right here, where phi of t, the phase, is equal to the integral of this d of t. So recall that if you put a signal d of t as an input to your frequency modulator, the output phase is the integral of this input. Okay? And we have this result for phi of t. So that's equal to 4 pi t times fd. Fd is the frequency deviation. And we substitute that for this delta, this d of tau to your expression right here. And you have this expression for your phase. By integrating, the abrupt changes in your the abrupt changes in this inherent in this d of t will be removed. So for example, your abrupt transitions from your square wave, for example, becomes a triangle wave. Okay? So something like that. So with that, that means the phase of your signal is continuous by removing the discontinuities through integration. Okay? So by definition of g of t, note that the area of that pulse is 1/2. So if we consider the time interval, okay, this time interval, your phi of t would become this expression. The integral will just be the sum of your past symbols times 1/2. This is the area of g of t. And your current symbol multiplied by the integral of your pulse shape. Okay? So we distribute that. And we have this expression for your phase phi of t. So basically, your phase phi of t is a function of the past symbols, past symbol inputs, and your current symbol input right here. So it sounds like it has memory. Okay? It is actually a modulation in memory. So let's define the state of your modulator and how does it transition. Okay, first, looking at the terms, let's define the sum of all the symbols be theta sub n. Okay? So theta sub n is pi times what we call h, the modulation index. It's defined as this. Okay? So theta n is the accumulation. So accumulation of all the symbols that has been transmitted. Okay? So you let the symbol accumulate, it results into a terminal phase theta n. And this represents the input of our, the current input on our modulator. Where beta is, since d of t is assumed to be rectangular, then beta is this piecewise function right here. It's 0 if t is less than 0. It's this value, which is ramping up, okay, from 0 to t, and it stops at 0.5. So the plot is something like this. So this is the time t, and the plot is something like this. This is your beta of t. Okay. So what happens is that if this is the input, as compared to your FSK, your CPFSK has a very smooth transition as compared to your FSK right here. So the FSK has very rough transitions. Your CPFSK has very smooth transitions. And because of this, we can infer that the frequency spectrum of CPFSK rather has a less leakage compared to your FSK. Excuse me. All right. So some notes, we can analyze our CPFSK using the equivalent bandpass signal. Right. We considered the complex baseband signal. Its bandpass equivalent is just this. So it's in a cosine carrier. The phase phi of t is inside that cosine carrier, the instantaneous frequency of your FSK is, you get the derivative of the phase with respect to time, right, and divide that by 2 pi, you get this expression for your instantaneous frequency. And simplify that, we have this expression for your instantaneous frequency. Okay? So it's equal to h over 2t a sub n. And the peak frequency deviation, so f sub d, is equal to h over 2t. And you can see that this h is equal to 2fdt. So let's look at a special case of your CPFSK. We call it the minimum shift keying. So your binary signaling scheme, so we use a binary signaling scheme with the symbol +1 and -1 when your h is set to be 1/2. So that would mean your peak frequency deviation is 1 over 4t. And that results into the symbol rate divided by 4. Okay? The instantaneous frequencies will have two values depending on the symbol. You have Fc plus Fd or Fc minus Fd. If we take the difference between these two frequency points, we can see that their difference is 2Fd, that is 1/2 your symbol rate, which is the condition that we need to make FSK signals orthogonal. So recall that two signals of different frequencies are orthogonal if their frequency spacing is an integer multiple of the symbol rate. Okay? So integer multiple of 1 over 2t, half the symbol rate rather. And this minimum shift keying case actually satisfies that. Okay? So one way to view the states in your CPFSK signal as a function of time is that we use the phase tree. So this is the phase tree. It shows all the possible paths of a phase of your CPFSK for a binary CPFSK starting at phi of 0 is equal to 0. So we start here. The list of possible paths that this phase takes is, well, you can see it right here. Okay. All right. So these are all the possible paths from here to here to here, then going up, etc., etc. It could be here, always going up, and then it goes down, and so on and so forth. There are a lot of possible paths, basically. So for example, so just you can see it, for your MSK that has a data sequence +1, -1, -1, -1, +1. Okay. For a data sequence of that, so what happens is, starting from 0, alright, starting from 0, we increase the phase from 0 to 0.5 pi. So that's from here to here. Okay. Oops, sorry. From here to here, and then decrease, 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 and then increase. So this is an example of your phase tree. So there you go. So it will just keep on repeating in this slide. But what happens here, what you see here rather, is very difficult to imagine, or very difficult to fathom if you have, if you go along, as you go along in time, your phase tree actually increases in size. Okay, so that's why we can use the phase trellis instead. So what is the phase trellis? The phase trellis transforms your phase tree by limiting the number of by limiting the phases. Okay? If we constrict the phase from 0 to 2 pi, your phase tree becomes the phase trellis. And for h equals 0.5, we have this kind of trellis right here. So your 0 can transition from to 0.5 or 1.5. Your 0.5 pi can transition to pi or to 0. Your pi can transition to 1.5 pi or 0.5 pi. And your 1.5 pi can transition to 0 or pi. Okay? And from the earlier example, the phase trellis path would look like this. So it will increase in frequency first, then decrease, which is just an increase to 1.5 pi, and then decrease again, and then increase. So as you can see, this is the path of your MSK with the following data sequence. Okay? And finally, if you have a system with states, then you should be able to look at it in terms of a state diagram. So in this case, as you can see from the trellis, we have 4 states, 0, 0.5 pi, pi, and 1.5 pi. Okay? So the state diagram would look like this. So for example, if your input is +1, your final state would increase by half a step times pi. Okay? If it's -1, your phase will decrease by half a step, 0.5 pi. Okay? So we can still use the phase diagram for this. If you know the phase trellis, or if you can see the phase trellis, you should be you should be able to construct the state diagram. Okay? So in general now, if we assume that our modulation index is m over p, where m and p are co-prime integers. So what does that mean? It just means that h here is rational, okay? So h is a rational number. So don't be afraid. The total number of states is p if m is even, 2p if m is odd. Okay? So that is actually shown here. Right? So if that is the case, if h is m over p, or if h is rational, then the terminal states of the phase, if m is even, is in this set. If m is odd, it's in this set. Excuse me. So if you're given the modulation index, you should be able to count and list the number of states of your continuous phase frequency shift keying. Okay, and we'll stop the lecture here. What to expect in the next lecture? Well, we'll be extending this CPFSK to a general case. So there's actually a general case from your CPFSK. If you look at CPFSK, we're actually looking at very specific examples, right? So we're actually assuming, first and foremost, we're assuming a rectangular pulse that has a duration and amplitude. So what if the duration extends to, say, 2t? What would happen to the signaling scheme with memory? Right? So something to think about. Right? So that is the end of this part of the lecture. That's part 1 of your lecture 5. If you have any questions, do not hesitate to leave a comment in the comment section below. Again, I will answer it as soon as I can. Thank you for listening. I'll see you next meeting.